Oh, now I can hear me though.
You can't hear you?
He can't
Yeah,
hear himself.
now
You're
I
getting
can
an
hear my
echo.
own echo, which I didn't before.
Oh. Hmm.
I mean, it's not too horrible, but a little bit weird.
Okay.
I mean, try. No, I think it's better. Did you change anything?
I didn't change anything.
Okay. So it was just for like a minute.
Okay.
Okay. All right. Maybe not to say figure out its echo cancellation. All right. Okay. So I got the recorder running. So we'll have video with dialogue, and we've got the slides, and I think we can start. Is everybody here? No, still a couple of people drifting in. So we'll start at the appointed hour.
Or
Okay.
At the unofficial appointed hour.
like the academic convention of the appointed hour.
Yeah, exactly. Exactly. It's a break with tradition. What time is it there? 10 p.m.?
Yeah.
11 p.m. Okay.
You're bringing me. I mean, I'm not doing any Friday partying now.
Yeah, right. You should have like a beer or something.
Yeah, to make a great impression. On
Yeah, absolutely. Absolutely. Something to aspire to.
I have Hamburg hipster Coke instead.
Okay, I think we've got everyone going. So welcome to week 10? 10? Yeah, I think it's week 10. Just a few more weeks left now, and this week we have another guest. Carl Friedrich Bolz is joining us via Skype from Germany. Which city are you in, Carl?
In Hamburg.
In Hamburg, okay. Where it's 11 p.m. So thank you so much for deigning to call and do this at such an ungodly hour for a lecture. Carl has been working on PyPy for 5 years, 6 years?
No, it's more like 11.
11! I didn't even know the system was that old.
I think, yeah.
And has written and co-authored a number of, I think, very good papers on the techniques of tracing and meta-tracing. I gave you a couple of things in the reading last week, suggested you take a look at. The one that you really absolutely should have read was the hot path paper, which is the basis of tracing, and hopefully is enough setup for you to get the points of meta-tracing, which I think is a very cool idea, and not the easiest thing to get your head around, though. So today we will hear all about that. I will get out of the way and leave the floor to Carl. Thank you.
Thanks a lot, Mario, and thanks for inviting me. So I'd like to start by just encouraging everybody to interrupt me at any point. I mean, if I start speaking completely incomprehensible nonsense, there's not much point going on. So just like tell me somehow, and I'll try to hear your question. So what I'm talking about today is, Mario already said, a project that I've been working on like for quite a long time now. And let's go to the second slide and the third slide, which is basically a sort of slightly different approach to constructing virtual machines than the one that is typically taken, and I guess also the one that you've been taking in your exercises so far. I mean, since you're sitting in that course, you already know that a lot of languages are basically now executed by virtual machines, like Java, .NET, Python, all the hip dynamic languages, JavaScript, of course. And most of the VMs that are actually used in practice, all the production virtual machines, are written by hand in C or C++ by large groups of people or small groups of people. And VMs, as you may or may not already be in the process of discovering, are actually not very straightforward pieces of software. So they can be quite sort of tedious to write, and they can take a long time to get the bugs out, and it can be costly in terms of the manpower that you need to like get them to an interesting point. And this is particularly true if you have a sort of very complex dynamic language like Python or JavaScript or whatever. Of course, next slide, please. Of course, a very important goal of virtual machine construction is performance. And since interpreters are often not fast enough for the applications that virtual machines are used for, the virtual machine needs some kind of just-in-time compilation system to bring that performance to an adequate level. And this is, again, particularly true for dynamically typed languages, where not a lot can be figured out about the program in advance by just looking at the program source code. So what does the architecture of a virtual machine look like? So I made this nice idealized diagram. The VM, of course, needs some way to express the language semantics of the language that is supposed to run on top of the virtual machine. And then, there are these nice proper boxes. So there's another component that's the JIT compiler that will basically take programs in the language and turn them at runtime into machine code, taking into account runtime feedback or whatever. And then I made another nice separate box, which is basically the optimizer that takes whatever intermediate representation that it uses, applies a number of transformation steps to hopefully improve the performance further. And all that is sort of embedded in something I just called general runtime, which contains stuff like a garbage collector or integration with the operating system or the a threading model or whatever. I'm not really going to talk much about the runtime part, so I left that slightly vague. Okay, so this is a nice theoretical model, and the problem is that in practice, this nice component model is not really true. Next slide, please.
Carl, quick interrupt. We see your slides, but I've realised we have no red channel on the second projector, so the colours are a bit off. If you have any colour distinctions that are important, we're going to have to read them out.
They're not awfully important.
Okay.
Can you like show me this slide number 5? Just use the webcam for a second, so I have a rough clue what it says.
Yeah, I realised when I saw your Smalltalk balloon, and it didn't look right.
I see. Also, basically, the JIT part is not particularly red at the moment,
it's
right?
It's kind of grey, yeah.
Okay. Okay, so that's fine. I think we'll be fine.
All right. So if you look puzzled by the pictures, then do speak up and we'll.
So there are colors, but they don't carry a lot of semantics. So
hopefully there isn't much semantics in red.
Right. I mean, the red is now gray.
Yeah.
So the JIT is gray, which is red in my screen, but I think we'll be fine. Right. Now we get away from the nice idealized picture and look at what a real JIT looks like. I mean, in practice, just-in-time compilers are very large and complex engineering artifacts that are maintained by like dozens of people, sometimes hundreds of people. They're growing over many years, they're in some cases decades, and the architecture is often very, very complicated with different bits of the system sort of completely tangled up in each other. And sort of that's what this weird diagram is supposed to show. Like the runtime is often deeply integrated with the language semantics of the implemented language, which is often very deeply intertwined with the JIT compiler. And of course, the optimizations and the language semantics are also mixed up because the optimizers need to know how the language works and so on. And this sort of big tangled mess means that it's very hard to actually change the language that the VM is running, right? So if there's a new feature, the new language feature that is supposed to be integrated, just implementing that can be annoying because there's some sort of optimization that depends on that feature not being there in a corner that is completely forgotten, or like other random interactions between things that are very hard to perceive. And that is particularly a problem for languages that still evolve a lot, like JavaScript being one example. There are actually a number of new JavaScript features that V8 does not implement particularly efficiently, because doing that would be really hard. Like it would require deep, not deep, but let's at least say very annoying changes to all the rest of V8. Another problem is, next slide please. And another further one, so we're at slide 7. Another problem is that, of course, there's not just one VM. So, there are many different VMs, and most of them share absolutely no infrastructure whatsoever. So, every VM implement all the bits of the garbage collector, all the bits of a just-in-time compiler, of an optimizer, of a backend, and so on, again and again. So it would be cool, and the talk today is going to be about that. It would be cool if we could get away from this sort of tangled mess, from these tangled messes, and move towards an architecture diagram that looks more like the nice idealized boxes that I showed you at the beginning. And this is sort of the goal of the project that I'm going to tell you about now. Next slide, please. So the goal of this project is basically to separate out sort of different concerns that one has when implementing virtual machines. So on the one side, there needs to be a way to express the language semantics, obviously, of the language that is implemented. On the other hand, one can imagine that sort of a lot of JIT compilation issues are completely independent of those language semantics, or could be at least. And there could be a set of completely generic optimizations that are sort of shareable amongst a large number of virtual machines. But then it's of course not really realistic to believe that all optimizations are expressible in a completely language-independent way. So there likely also have to be some kind of language-specific optimizations. But it would be cool if basically those four things can be separated and reused as much as possible. And next slide, please. This is indeed the goal of the RPython project and the Python project. So what is RPython? I mean, the word RPython stands for Restricted Python, and it's basically a programming language that was designed to write interpreters in it. And it's called Restricted Python because Python itself is quite dynamically typed, and RPython is restricted in such a way that it's possible to take an RPython program, analyze the whole source code of the program, find out the type for all the variables that occur in the program, and then transform that program into C code, right? So it's basically, RPython is a subset of Python that is compilable to C. And so basically what you do to implement your language with RPython is you write an interpreter for the language in RPython. And then the RPython translation toolchain comes, takes your interpreter, produces C-based VM. And in that transformation process, a number of features are added to your interpreter that are not really explicitly in the interpreter. And the most obvious one is a garbage collector. So the interpreter itself is written in RPython. RPython is a garbage collected language. C is not. That means when translating your RPython program to C, the garbage collector needs to be somewhere. It needs to come from somewhere. And it comes basically from a transformation step that while the interpreter is being transformed to a C program, also sort of builds in a garbage collector to the side. So we've used this language for a number of, to implement a number of interpreters, and the most mature and the one that I will talk about most today is called PyPy, which is a Python interpreter in RPython, which is also obviously where the name comes from. And actually, the RPython project, I mean, sort of, the order in time is really the other way around. The original project was the PyPy project, and in the development of the PyPy project, it became clearer and clearer that the RPython language that was implemented basically only as an implementation vehicle was also very useful for implementing languages for like virtual machines for other languages. And as we already hinted at, it's a pretty old project. It's like 13 years, something like 13 years old, I think. And it has like received quite a bit of funding, and a large number of person years have gone inside, basically. Right, but so far, what I've told you is not actually that interesting. It's basically a garbage collected language that you can use to write interpreters, and then compile them to C. I mean, so far it's like any other language that's garbage collected and that can be compiled to C. But what makes RPython interesting, next slide please, is the way that we also are able to integrate a just-in-time compiler when taking an interpreter and transforming it to C. So, and the approach how to do that is called meta tracing. And how meta tracing works, I will explain in a lot more detail, sort of in a few slides. But the basic principle is that you take this interpreter written in Python, it's compiled to C, and while the Python interpreter is transformed to C, there's another component inserted into the final C executable, which is a metadit, which is basically a generic reusable just-in-time compilation infrastructure that can be used for basically any interpreter that's written in Python. And so the metadit contains a lot of sort of the generic just-in-time compilation infrastructure that you would expect. For example, there is a number of backends for various machine architectures, like whatever, Intel, ARM, Power, and a few others. There is integration with the target operating system that the JIT compiler needs. For example, getting executable pages of memory from the OS, stuff like that. And there's also integration of the JIT, the garbage collector that is also inserted into the final executable. So this insertion of the JIT compiler into the final executable is mostly automatic, but it's not completely automatic. So the interpreter author needs to help this process by basically adding a small number of source code annotations into the interpreter to sort of tell the process like how the interpreter works a little bit. But that's not actually a lot of code. So there's like a couple of like 10 lines or something like that that need to be added to the interpreter to make the insertion of the JIT possible. And how that works, we'll see an example soon as well, but the basic idea is that it's necessary to tell the process where the main bytecode dispatch loop of the interpreter is and which variable in that bytecode dispatch loop stores the program counter. Right. Next slide, please. In addition to this generic reusable JIT, there is also a generic reusable optimizer that is a bit tangled up with the JIT, but not too much. And anyway, it doesn't really matter when you're just writing an interpreter in Python because you can just reuse the optimizations that are already there. And the optimizations are sort of what you would expect. I'll talk a bit about them later, but there's nothing too fancy there. Right, so now next slide. And the next one immediately, like 13. So let's talk in some more detail how this meta tracing JIT works. So you read the hot path paper, so you will know most of that, but I will still basically recap it. So one of the cool ideas from when tracing JITs were invented by Dynamo and HotPath was the idea is that if you have an interpreter for language, there's this idea of adding a very simple component sort of to the side of the interpreter that is the tracing JIT that makes it possible to use that interpreter to produce machine code for the programs that the interpreter runs. And that is basically the tracer. Next slide. So you take the interpreter, you add the tracer and the optimizer on the side, and they can help you to, instead of just interpreting, also producing machine code from your program. And the way that works is that you start out running your program completely regularly as you usually do it in the interpreter by just interpreting it. So the interpreter happily executes the bytecode of the program, but while doing that, it also does a little bit of profiling to figure out which parts of the program are executed particularly often. So another big insight of the tracing JIT approach is that in order for a program to run for a long time, I mean, it's not such a, I mean, the insight itself is easy, but then sort of what follows from it is not completely easy. But the insight is, in order for a program to run for a very long time, there's usually some kind of loop that is running many iterations. So the idea of a tracing JIT is that it tries to focus its compilation efforts particularly on these long-running loops within a program. So when the interpreter starts out running the program on top, it basically does a bit of profiling to figure out which loops in the program are the loops are executed often. And it does that in usually very simple ways by simply having some kind of counter per loop, and then you increase, per loop iteration, you increase the counter, and if the counter goes over some threshold, you say, oh, I've already run that loop 1,000 times in the interpreter, it must be an important one, so it's probably worth to focus some computation effort on that loop. And so once the threshold is reached, the interpreter tells the tracer, oh, over there, something important is happening here. It's probably worth to start looking at what I'm doing. So what happens then is that the interpreter keeps running. So it keeps executing that loop, which should be the next iteration, but the tracer is also enabled. And what the tracer does is basically just, the tracer keeps a log of the operations that the interpreter executed to run the loop. And usually that log is really simply in the form of the bytecodes that the interpreter executed when executing the loop. So that goes on for a while, so the tracer simply makes a longer and longer list of bytecodes that were run while executing the loop. And in the end, the loop is, at the end of the loop is reached again, and the loop would start back at the beginning, and at that point the tracer says, okay, I recorded one iteration of the loop now, I'm now going to turn that into a piece of machine code, optimize it, turn it into a piece of machine code that now corresponds to the loop that the interpreter was running. And actually, so one of the really interesting things that happens sort of as a side effect of this approach is that you automatically get inlining of all the functions that are called in this loop. Because for the tracer, it really doesn't matter at all that there is a call instruction in the loop. It will simply ignore that call instruction and instead record the operations, the bytecode operations that were executed when running the call function. And in that way, all the functions that are sort of called from that loop are simply inlined into the trace as well, which means the tracing JIT sort of in the way that it's constructed, inlines stuff very aggressively into a program. Okay, let's look at an example, because that was probably a little bit abstract. Go to the next slide, please. Okay, this is a completely synthetic example of an imagined tracer for a Python-like language. So we have this sequence of instructions, and let's assume that this sequence of instructions occurs in a commonly executed loop. So there's some loop body around that. But I wanted to sort of have something small. And so the tracer determines it's important to trace this bit. So it starts tracing, and and during the tracing, the value of the variable x is 6. So next slide. So the trace that is recorded looks something like this. There are all these guard instructions, and I'm going to explain to you what they are. Because there's actually, to execute an operation like x smaller than 0, this is supposed to be a dynamic language. So in order to figure out how to actually implement the smaller than operation, the interpreter first needs to look at the types of the arguments of that instruction. So at first it sees, okay, x is an int, it's 6. So to make sure that this is again true, the next time I'm executing the trace, it inserts a type guard. So it says, make sure that x is an int. And then the other operand, the same thing happens for the other operand. So there's another type guard that says, make sure that 0 is an int. It is obviously, but I mean, it's still recorded. And then we come to the if. So we execute the less than, and then there's an if based on that. So we record again with a guard that during the tracing of the loop, x was smaller than 0. It's not smaller than 0, sorry. And then we're in the second, in the else case. So we check again that x is an int, we check the 2 is an int, then we do the addition, and then we're after the else box, so we check that x is an int, check the 3 is an int, and do the other addition. Okay, and already we can see there's a lot of redundancy here. We check I mean, on the one hand, we check the types of constants. So the type of 0 is obviously always int. So those can just be removed by some kind of constant floating. And then we repeatedly check the type of x. So after we saw that x is an int once, we don't need to check that again. So the optimizer would turn that into, next slide, something much shorter. And then it might also fuse the two additions together to just like immediately add 5 and not first add 2 and then add 3. But the important guard that's still in there is the guard that checks that x is indeed not less than 0. Okay, so and we need to think about those guards some more. Next slide, please. So as we saw, every time the tracer hits some kind of condition in the loop, it needs to turn that condition into a guard. And the reason for that is, if later we turn the trace into machine and we run the trace, that trace is only valid. I mean, the trace is a linear path. It's just a linear log of operations. There's no control flow in that at all. So if we execute the trace later, and one of the if statements goes another way than the way it did during tracing, the machine code is not actually valid for the whole execution. And so all the places where the control flow could have diverged need to be checked with a guard to make sure that the control flow is indeed the same as when the trace was recorded. And so if one of these guards fails, then execution of the machine code that was generated cannot actually continue, because it would be a bad idea to just follow some random old control flow that we might have seen once. So if a guard fails, the execution of the machine code stops, and instead the interpreter is started again from the point where the guard failed and to go down the other path. And actually, one of the surprising things is that, and that is not necessarily obvious a priori, but one of the surprising things is that most guards don't fail. So if you actually do some statistics for real systems, and you look at how many guards ever fail, it turned out that 90 to 95% of guards never fail. And then of those that fail, a very large percentage fail only a few times, not very often. Right, but okay, so it's nice, quite often we stay on trace, but then of course sometimes there are conditions in a loop where both sides are equally taken, right? So there is going to be a guard for those conditions that fails. And tracing needs to, like the approach of the tracing needs to deal with such a situation as well. And the idea for that is, if you have a guard that fails, you basically increase some kind of counter to remember that this guard failed a number of times. And if that counter goes over another threshold, so if you say oh, this guard has failed like 50 times, it failed all the time, we need to do something. Because going back to the interpreter and then interpreting is slow. So what happens then is that the tracer will start tracing from the point where the guard failed, produce another piece of trace, like another linear path that takes some other control flow path through the loop, and then produce machine code for that, and patch the original machine code so that the guard failure that used to go back to the interpreter for the commonly failed guard now goes to the new piece of machine code. And then in that way, sort of in a piece-by-piece fashion, we cover more, the tracer will cover more and more control flow paths through the loop, until in the end, almost all the paths are covered. Ideally all the paths that are actually taken are covered by traces. And then we don't actually need the machine code anymore. Right. Okay, so it may have been a little bit confusing how the tracer sort of goes from interpreting to tracing to executing. So on the next slide, I made a small sort of state diagram in which sort of states the VM with a tracing bit can actually be in any point. So when you start your VM and start running the program, as I said, the program will always be interpreted first. So we start at the upper left corner and run the program until the profiler in the interpreter says, oh, this loop over there seems to be important. So at that point, the VM will transition to the tracing component. It still keeps running the interpreter, but then at the side of the interpreter, there's also the tracer that sort of records what the interpreter does. And that goes on until the interpreter has run another loop of another full iteration of the loop. That means the trace corresponds to a loop. So the tracer hands it down to the optimizer, which will optimize the trace, produce machine code. And since the loop, the next thing that the interpreter would do is run another iteration of the loop. So immediately we can go from the optimizing component over to the machine code that we just made. We just jump there and immediately run the next iteration of the loop that we just traced in hopefully efficient machine code. And we will just keep like that. As long as the control flow doesn't diverge, we can happily execute a very efficient machine code version of that trace. Of course, I mean, usually it's not going to be an infinite loop. So at some point, either the loop will be left, which is done by a guard, or another path will be taken, which is done by another guard failure. So at some point, we will leave the running of the machine code on the right, and by a guard failure, and go back to the interpreter. And now there are basically two edges missing. One edge is kind of obvious. When we're in the interpreter, we're running along. At some point, we hit a loop that we already made a trace for. And then we can go directly from the interpreter to running to the running of the trace that we made earlier. Because of course, we're caching the trace and connecting it to the loop so that when we hit the same loop later, we can reuse the trace and we don't have to trace again. Right. And then there's another, like the only missing transition is we're in a trace, a guard fails, we're running a trace, the guard fails. We already know that this guard failed often before. And then we go directly from running the trace to tracing the path that starts from that failing guard and trace that until it hits another bit of something that we know and then basically patch in that side trace. Right. Okay, so this is the basic idea of how tracing works. And I think it's sort of a good idea to breathe in for a little bit because it's quite different from sort of the typical compilation approach, which is a method-based JIT where sort of the compilation scope is a single method and sort of just think for a moment. I mean, does that approach make sense? Are there any questions or?
I have a question actually.
Yes.
I've read a bunch of the papers and
okay.
I've never seen an answer to this question, so maybe you can answer it. What the situation that you describe works fine
Mm-hmm.
in the circumstance that each individual interpreted element has no internal control flow of any sophistication.
Mm-hmm.
But if you imagine a situation like, you know, Smalltalk having a bitbullet primitive,
mm-hmm.
and the bitbullet is one bytecode.
Right.
And you want to sort of trace your path through the implementation of that bytecode of that primitive.
Right.
How do you adapt the tracing to that situation, or do you just not do that?
That's an amazingly good question. It will also actually lead very directly into what makes meta tracing cool. I think there are two answers. What the tracers typically do is that for a lot of the bytecodes, they then have special logic that says, I know if I trace this bytecode, I also should record some extra information because the bytecode has some internal control flow, and I need to sort of explode that bytecode into synthetic somethings, right? A very good example is really already something like an addition. Right? In Smalltalk, it kind of maps to a method call, but there's usually some fast path for ints, right? So already you want to explode that into, oh, does it happen to be 2 ints? Then go do this special path thing. If not, just do the normal method with them. But basically the way it's done is that in the tracer, there is a special piece of logic for every bytecode that has internal control flow to do that, right?
Okay.
And actually that is a very good, I mean, yeah.
Okay.
It will be a great segue to the next slide, but let's see whether there's anything else that I can answer.
Any other questions? questions. Yes.
It's like if you do that, you're gonna, if you have really a loop that lives for a long time, then you're gonna fill up your cache with iterations. Is there a way to like turn that back into a loop in the assembly somehow?
Yeah, right. Okay, so what happens is you don't really trace all the iterations of the loop, right? You just trace one.
Okay.
And then basically every trace, every simple trace is really always a loop. So every trace that you make always, by default, always ends with a jump back to the top. Right?
Okay.
So, in the simple model, all the traces are loops. And then only those traces that don't actually start in the interpreter, but that start at side exit, they are a bit more complex. But in the very basic tracing model, all of them are loops, and you will never sort of trace many iterations. You will always trace exactly one. Does that make sense?
How are the iterations called? How are the iterations?
Sorry?
How are the iterations launched? Do they have to go back through the interpreter? Or back in?
No, it's really just you will really emit a jump back to the instruction that, like to the first instruction in the trace, right?
Okay.
I mean, that's really the only way that it becomes efficient, right? If you need to sort of jump back between JIT and interpreter for every iteration, all like you would have a lot of overhead. Is that okay?
Yes.
Yep.
What happens if your loop contains a loop? Do you throw away the first loop start?
So there are many answers to that. I mean, so that kind of starts to be the area where the tracing hits differ a lot. The basic idea is that you basically turn the loop inside out. Because the loop that is actually the hottest in the nested loop situation is the inner one, right? So what happens is that you make a trace for the inner loop, and then there is a guard in there that says that is for the situation where the inner loop is finished. And then since the outer loop also runs often, that guard fades a lot, right? So at some point we will start tracing from there, and that trace corresponds to one iteration of the outer loop, which will then jump back to the inner trace, basically, right? So in that way, the inner loop becomes the important loop, and the other one is this weird sidebar.
Right.
But this also starts to be the place where tracing JITs are not ideal, right? So if you have very complex control flows with deeply nested loops and a lot of very complex conditions inside where the paths through that condition nest are very unpredictable, this is the kind of situation where tracing JIT does not produce the best code, right? Okay.
How would you consider method calls or recursive calls? Do you consider this a loop when you jump back?
Right, that's another excellent question. So that again depends a bit on the system. So in PyPy we don't. In PyPy it really gets turned into a piece of machine code that does an actual call on the assembler level so that the CPU stack is used. But then, for example, I'm not going to talk about it today, but we also have basically a racket scheme JIT, and there it's very important to actually turn recursion also into a loop, basically, and that's actually not that hard. So if it's tail recursion, it really simply directly corresponds to a loop. But if it's really recursion that goes up and builds a stack and then needs to go down, we'll turn it into two loops. You turn it into one loop that builds up stack frames until you reach the final condition, and then you will build another loop that sort of removes stack frames, right? But sort of different tracing JITs have sort of different approaches there. There was another question on the other side?
Oh, the same question.
Oh, okay. So, should we continue?
Yeah.
Okay, let's do that. To go back to Mario's question, as I already said, in practice, the model is not so nice that you keep your interpreter and you have a completely pure box at the side that just sort of peeks what the interpreter does and makes nice code out of it. Because in practice, a lot of the logic of what happens in the language needs to be repeated in the tracer. Because quite often, bytecodes have inner logic. So the tracer needs to sort of repeat the semantics of a bytecode, both in the interpreter and then again in the tracer, to sort of expand it into like micro instructions or to optimize it better or stuff like that. So in practice, the nice picture is again not true, but it's again quite messed together. And another problem, I mean, of course, the problem of needing to start from scratch for every language is also not solved, because every language tends to have its own bytecode set. That means if you want a tracer for a language with a different bytecode set, you again need to start writing that tracer from scratch, basically. And that is this problem of not being able to reuse the tracing component is the one that meta tracing solves. Next slide. I'm on slide 19. Are you as well? Okay. So meta tracing, and I mean, the idea of meta tracing is a little bit mind-bending, but actually it makes sense when you start thinking about it a bit. The idea of tracing is that, okay, the problem is we had to write a new tracer for every bytecode set of every interpreter. That's annoying. And we had to replicate sort of a lot of the semantics of a bytecode within the tracer. That's also annoying. So what do? What we do is we don't actually place the tracer next to the interpreter, but we place the tracer sort of in the figure below the interpreter, which means we make the implementation of the interpreter completely transparent to the tracer. And that means we don't actually trace iterations of the user program, but we trace really the lines that are executed within the interpreter source code, and trace what's going on there. That's also, I mean, you may not be able to see that, but that's also why the color of the trace changed from pink to green, because we no longer have like
nothing in pink or in green.
Right. Okay. We changed it from gray to a slightly different shade of gray. Right. So anyway, the trace will now no longer contain bytecodes. It will now contain operations that correspond to the source code of the interpreter and the things that are going on in the interpreter. That means the operations in there are a lot more fine-grained. Okay, so what you know, since I looked at your exercises, is that simple interpreters are actually big loops. I mean, particularly bytecode interpreters. In C, they're a big, like, endless loop that just says, give me the next bytecode, and there's a switch over what bytecode it is, and then you go somewhere. So this is great, right? Tracing this loop is perfect, because we have a loop, and we spend all our time in that loop. So one of the conditions for when a tracing helps is already met. We have a loop. But then the problem is, the control flow through that loop is not actually very predictable. Like, let's say we execute some programming in our bytecode interpreter, and we execute addition bytecode. The probability that the next 1,000 bytecodes are also addition bytecodes is very low. So the control flow through that bytecode dispatch loop is not following a very predictable path, iteration after iteration. So it appears like we are stuck. Like, it appears like tracing the interpreter is an awful idea, because we never stay on the trace. And the insight is that we don't actually just trace one iteration of the bytecode dispatch loop, but we trace many. And we trace so many iterations that the length of the trace matches up to a loop in the program. So that means we start tracing when the interpreter executes some kind of bytecode that says, here is where the loop starts. And we trace many iterations of the bytecode loop through many different bytecodes until we hit a jump back that goes back to the beginning of that loop that we started tracing, and then we stop. And that means our trace now contains operations that corresponds to source code level operations of the interpreter, but the length of the trace still corresponds to loops in the program that that the user executes. That is running on top of that interpreter. And in that way, we get our predictable control flow back. Because since the loop that is running on top of the interpreter likely will have predictable control flow, we get again a trace where we can sort of likely stay on the trace for many iterations of that trace, which corresponds to many bytecodes, but one path to the user program. Okay, so again, let's pause and see what questions there are.
I have a question.
Okay.
No, I'll save it for the end. I'll save it for the end.
How do you detect the loop back? Right.
Mm-hmm.
So if you don't know anything about the final target language semantics, so how do you know that you're starting over? You're just constantly doing like a pattern matching on your
Right.
trace?
So that's one approach, and that's of course, we haven't specified it. So what we do instead is we ask for some level of help by the interpreter office, and that will be again a very amazing because it will help me get to my next slide. Let's go there. So what we ask the interpreter often to do is indeed to give us some information about the interpreter. Because, okay, we know that the interpreter is likely a loop, but quite likely the bytecode dispatch loop is not the only loop in the interpreter. There are probably other loops in the interpreter, like for example bit. And so it's not necessarily the case that we should try wildly figuring out which of the loops in the interpreter are the bytecode dispatch loops. So what we ask the interpreter of instead is to basically add a little annotation in the source code that says, this is the loop that counts, focus on this one. Right, that's the one piece of information that we ask the interpreter author to give. The other piece of information that we ask the interpreter author for is to mark the instruction that can lead to the closing of a loop at the user level. And let's go to the next slide, which is 21. So those are basically the two annotations that you need to add to this little fake interpreter that I sketched there. So at the top is the while loop, which basically loads an instruction, and then there's a switch, which is just a series of if statements for each instruction. At the beginning of the while loop, you need to say, here, like the name of there's this magic function you need to call, and that tells the JIT this loop counts. And then in the branch instruction, you need to call another magic function called can_JIT that is called only for those branches that can close loops. And branches can close loops exactly if the jump that they do goes backwards, right? Because in order a loop is basically a situation where you repeatedly execute the instructions of the same program counter. And that can only happen if the program counter decreases at some point. So basically, a branch, we need to call can_JIT at the branch instruction only if the jump offset is negative. Right? And with these two hints, the metatracing JIT has enough information to do some profiling, because it can basically, at the place where we do can_JIT, it can keep one counter per value of PC to see how often that program counter has already been seen. That's the first thing it can do. And the other thing it can do is it can start tracing if that counter executes a threshold, which means it can basically execute many iterations of that one loop until we hit another branch that goes back to the same program counter where we started. Is that, does that make sense? Cool. So, any other question?
So, with this approach, the generated trace would also necessarily have the instructions for fetching the next bytecode from the stream, right? So
Yes.
even if you're in a loop, you're still going to be fetching each bytecode and have a guard to ensure that it's the same bytecode that you saw before if nothing.
Yes, absolutely. So you start out with exactly that problem, and it then, I mean, it's then the job of the optimizer to get rid of that overhead. And it's kind of obvious how that works. Because, so in Python, strings are immutable. That means if you have a constant bytecode string and you read a program, you read an instruction at a fixed program counter, you can constant fold that read. And then the switch to figure out what the correct next bytecode is can also be constant folded. So that way you get rid of all the operations that operate on the program counter and on the bytecode string, right? Patrick, did you also want to ask something?
I'm still a little confused about after you collect the trace of opcodes, when you loop back in the user program, how does the tracing JIT know to, like, I've collected the trace, I want to start executing my native code?
Well, basically, every time the tracer hits a backward branch, it checks whether the target of the branch corresponds to the beginning of the trace. If that's the case, we close the loop. And in that case, we can hand the trace, we will basically add a jump to the end of the trace, saying jump back to the beginning, we hand over that trace to the optimizer, and then there is some annoying code that then will jump to that newly generated machine code.
Okay.
Right? And we can always immediately use that machine code because we are still in that loop that we just traced. Right?
Okay. So, so do you map the index in the bytecode to traces?
Yes,
Okay.
yes.
Okay.
So basically, per program counter, we keep a count, an entry count, and an address if we already made machine code for that loop, right?
Okay.
So in the interpreter, if we hit this energy bit, there's some code automatically inserted that says, do I already have code for that? And if yes, just go there.
Okay.
Right?
Okay. So in a language like JavaScript with eval, there's another mechanism to take care of that.
That is not actually clear that it's a problem. So, I mean, eval is a problem because you need to invoke the parser, and if you do it often, it's just not going to be very efficient, right? But the tracer doesn't, the meta tracer doesn't actually have a problem with eval, because it will simply trace into the parser, and it will probably pretty quickly say, there's absolutely no use in inlining everything here. So it will just generate a call that basically goes to the parser and does the work there, right?
Okay. Okay.
And Mario, to get back to your bit question, I'm not really sure it makes sense to trace into bit because bit contains another complex loop, so it's not that clear that you would win anything by inlining all of that, right? But actually, if you remind me, the Potsdam group has written a paper about their RPython-based Smalltalk that indeed has a bit, has some interesting experiments around bit.
Okay. Thank you.
Okay, where are we? So let's go to the next slide. I think we said all that. Right. Actually, I'm referring back to one of the other questions, which is all the bytecode operations are still in the trace originally. There are more vestiges of the interpreter present in the trace. And another very obvious example is stack manipulations. Because if the interpreter is stack-based, then the trace will basically contain operations that say, oh, read the stack at position I, store null there, increment the stack counter, the stack pointer, and so on. And it's actually important that the optimizer that it has are good enough to remove the overhead of that static manipulation, because otherwise the machine code that you generate is just not going to be very efficient. And then the other thing that I kind of want to hint at, but not really go into much detail, is that there is a lot of sort of annoying technical details that are involved, particularly around sort of going from the interpreter to the tracer, and even more annoyingly going from the tracer back to the interpreter. Because if a guard fails, it's possible that that happens several inline levels deep. And sort of going from that point where sort of the tracer just inline everything, but the interpreter would really like stack frames and infrastructure, going from one place to the other is technically rather annoying, but it's not, I mean, it's just a matter of programming. It's not that deep somehow. And also, despite these technical problems, sort of the separation between the interpreter and the JIT is still maintained, right? Because all the messy technical stuff is hidden in the JIT, and as an interpreter also, you just don't need to look at it. Okay, right, next slide. So as I said, the tracer needs to contain sort of, or it does contain a number of all the typical compiler optimizations that you would imagine. So there is stuff like constant folding, there's stuff for optimizing heap accesses, there is dead code elimination, there is strength reduction, there's all that kind of stuff. So they're all sort of very unsurprising in a way, which of them are there. The thing that's kind of interesting is the fact that they're all rather easy to implement. So one of the things that makes a tracing JIT fun is the fact that the optimization stage is really trivial, because the optimizer only needs to deal with a completely linear piece of trace. So there's never any complex control flow that the optimizers need to reason about. So all the optimizer does is basically have one or two passes up and down the trace, and basically just removing operations in there. And that makes sort of the optimizer stage significantly easier than in a method JIT, where you need to deal with control flow merges and jump backs and jump somewhere completely different and stuff like that. So the only optimization that is sort of quite different from what many other JITs have is what's called allocation removal. And that optimization is very important in the context of a dynamic language, because dynamic languages tend to allocate a lot of memory, and I think that the example language that you're using in your exercise also has that property. That is done for a very simple reason, because primitive objects like integers and floats need to be boxed, which means they need to have a little heap cell, like a little piece of memory on the heap where their value is stored, in order to make them look like other objects. And that means every arithmetic operation actually needs to look at two of these heap cells, read their content, do the operation, and then make a new, go to the garbage collector and say, I need a new piece of memory for the result. But the fact is that if these memory cells for primitive values, they often have really limited and completely predetermined lifetime. And that becomes completely obvious if you look at a simple arithmetic expression like a plus b times c. So if you run a plus b times c in an interpreter, what happens is that and they're all in, let's assume they're all in. What happens is that the interpreter will check the type of b, it will check the type of c, it will read the content, it will do the multiplication, and then it makes a new box on the heap, which it then passes to the next operation, which is a plus that intermediate result. And then that will do the same dance again. It will check the types, will do the addition, will make a new box. But at that point, where the result of the whole expression is produced, the box of the intermediate expression of b times c is dead. So the garbage collector can collect it, but of course it still works to like get rid of it. So one of the very important and very dynamic language specific optimizations that we have in ArcPython is basically a pass that can go through the trace. It looks at all of the mallocs that occur in the trace, and it can remove allocations that have a short predetermined byte frame. And that means, in particular, that all the intermediate results of arithmetic, like big arithmetic expressions, get removed completely. That means if you have a loop that mostly does numerical calculations, in an interpreter, lots and lots and lots of garbage is going, like memory garbage is going to be generated. But then after tracing, most of these allocations are completely removed, and which just simply increases the performance significantly. But anyway, this is just sort of a little aside. I'm not going to talk much more about that now. Right, okay, so we're actually in a pretty good place now. We sort of, we talked about how the metadit is sort of inserted into the R-Python interpreter, what the interpreter also needs to do to tell the JIT where the main loop and where the jumps are, and stuff works, right? Pretty good. The problem is, and we have some nice generic optimizations that reduce a lot of overhead. But the problem is that the generic optimizations cannot actually make use of a lot of properties of the language that the JIT doesn't know about. And so let's go to the next slide and one further. So why is the JIT a good idea? Actually, I think you can answer that. Why do we use JIT at all? Why don't we just use static compilers?
Come on, people, don't let me down.
What? I have to do something.
The compiler can use information from the current execution of the program. So it can
Right.
use some statistics to make it better.
Exactly. Yes. Absolutely. Basically, the power of the JIT comes from being able to look at what the complete run of the program did and feed that information back into the compilation process. And this is something that the system that we described so far is not doing that much. It's doing it a little bit because it does, it chooses control flow that happens to be run often in the current process, but it's not really doing anything very advanced. And the reason why it can't is because while the semantics of the language are completely clear to the tracer, but the tracer still doesn't know sort of the typical ways that the language is used in practice. And that's actually a not completely obvious point. I mean, one could think that, okay, the tracer can observe the interpreter. The tracer knows perfectly how the language works. But that is still not quite enough information to actually do any good optimization, because a lot of the ways that a language is used are not necessarily obvious from the semantics of it. Okay, that was hyper abstract. Let's be quite concrete. I mean, in most a very important optimization for optimizing object-oriented languages is the observation that most method call sites are monomorphic, which means that for most call sites, one very specific implementation of a method is called. And that is actually a very surprising result. That is not present in the semantics of that object-oriented language at all. In theory, it's conceivable that every single call site will call thousands of different methods implementations. But that does not seem to be the case for any realistic programming practice. So what we need is a way for the language implementer to be able to sort of communicate these expectations about how a language is used in practice back to the tracing JIT. And for that, because that information is really not present in the interpreter source. And for that, there's basically a second set of hints. So the first set of hints was for pointing out where the bytecode dispatch loop is, and the second set of hints is responsible for basically encoding knowledge about the language that goes beyond how to execute the language, and that goes into how is the language typically used. And again, let's really look at that method called something that I started talking about on the next slide, 26. So as I said, at one method call site, it's quite often the case that always the same method is called. I think you will actually use the same common property of object-oriented languages soon in your own exercises. So here is a very, very rough sketch of what implementation of a method send could look like in an interpreter. So basically the send consists of two parts. On the one hand, there is the lookup. And the lookup basically takes the class of the object that we're sending a message to, and it takes the name of the method, and then it will walk up or down the inheritance hierarchy of that class and look at every level whether the method of that name exists, and if it will return the first one. And the details I just left out here, they're not that important. And then there is another function send here, which actually implements sending of messages on the interpreter level. And it takes an object, it takes the name of the message, and it takes like some list of arguments or some objects of arguments. And so the way it's implemented, it simply it asks the object for its class, and then it looks up the method with the given name on the class, and it has a method object, and then somehow on the interpreter level it will use some mechanism to actually call that concrete method that was passed. So what we know, because we did some statistics, is that quite likely the method object the class object that we see at a specific send place where send is called in the interpretation of the program, the class is always going to be the same. And we can communicate that information that the class is always the same with a hint, which we see on the next slide. And that hint we call promote. And what promote basically says is, I expect the argument of the call to promote to only contain a very small number of values at that place in the trace, right? So it tells the JIT, I'm pretty sure that at this place, you will only see 1, 2, or a small number of classes when you actually run the trace here. And so during interpretation, the promoting is just ignored. But when we trace, the tracer will use the promote and insert a guard at that point. And that guard says, check that the variable class contains this value. And the value that it uses to compare the variable against is the concrete runtime class that was seen during tracing, right? So promote is basically a mechanism to be able to feed values from runtime into the trace. So it can basically make variables constant. And of course, that's only a good idea if the variable class really only takes on a small number of values, because otherwise you introduce the guard that will just fade off, and that's never wrong, but it's not a good idea either. Right, okay, so now we know the constant value of the class. But what do we do with that, right? It still goes into lookup, and lookup is probably very complex. But now we can, let's assume we have a very simple language where you cannot actually change the inheritance hierarchy at runtime. You cannot add new methods at runtime. That means like classes are completely immutable. And in that case, we can add another annotation, which is on the next slide, which basically says that if the tracer sees a call to lookup with constant arguments, it can completely remove that call and replace it with the result that was seen during tracing. And we can only do that because, as I said, you cannot actually, I mean, in this fictitious language, you cannot add new methods at runtime. And now we're in a pretty cool situation, because now the code that is generated for sends contains a guard that checks that we still have the class that we saw during tracing, and then it immediately goes to calling the method that was seen during tracing, right? So with these two hints, we basically implement some kind of inline cache. An inline cache is basically only the simplest thing that you can express with these two things. They're actually surprisingly powerful, and in some ways, we're still, like, a couple of years later, we're still discovering fun fun things to build with these building blocks. But the building blocks are, I expect this variable to take on only a small number of values, and basically a way to define your own kind of constant folding, saying if you have a call to that function, constant folded if it's safe to constant fold it if all the arguments are constant. Right. Does that make sense?
So
Yeah.
the elidable annotation is like a purity annotation?
We intentionally did not call it pure. In fact, it was called pure originally, but there's actually a very legitimate use case for adding it to non-pure functions. And that is if the function itself does some kind of caching, right? So the function, sorry. If the function itself has some kind of memorization or something, then the function has side effects. It changes the memo. But that side effect is not externally visible. So if you call the function a second time with the same argument, you will get the same result back. Even though if you actually analyze the function with some kind of side effect analysis, you will see that it does stuff. So it's really, it's really okay to add it to functions that that are not really pure. Right? So that's why we didn't call it that. But basically, it's always safe to add it to pure functions also.
Okay.
And also so promote is always safe. It might generate bad code, but it will never generate wrong code. But elidable is not safe. And in fact, we have a checking mode that where you run your program slowly and check whether all your elidable annotations are sort of consistent. Right? Okay, there was another question?
You also need to promote the message name.
Sorry?
You also need to promote the message name.
That's a good question. Kind of. So in theory, you don't have to, because in the send bytecode, the message name comes somehow from a place where it's constant, right? Because it's somehow computed from out of the bytecode stream, so we know the bytecode is constant, we know that the program count is constant, so we get the message name. So the message name is usually constant. But then there are also, quite often, sends are used in generic ways in some kind of meta-programming setting. And there it may even be a bad idea to promote the message name, because it might really be a place where we call the send with very different message names, right? So I would say it's a little bit risky, because there might really be, in the interpreter, there might really be places that call the send function with message names that really are not as constant as sort of would be good.
In effect, the promotion of the message name would be in the decoding of the bytecode where it appeared as a constant. Yes.
Yes.
And not here.
But then I don't know how I guess in Smalltalk there's a send primitive somewhere, right?
Yes.
And there it would be bad to
right.
promote the message name, right? So indeed, that's why we don't do it in here, but we do it in the bytecode that has a constant message name. Right? Okay, any other question? Okay, cool. So actually now we're getting there. Now we understand how the meta tracer is inserted into the VM, and we also know how the interpreter author can add some extra hints to sort of language feature per language feature, improve the performance of the generated code. And actually that concludes the part of the talk about the meta tracing approach. So what I will talk about in the last quarter is basically talk a bit more about two small case studies, and next slide and the next slide. And I'm mostly going to talk about PyPy. So PyPy was really the reason why the whole project got started. So basically it was a couple of people that said, Python is great, but it has a slow implementation, and all the attempts to write a JIT has failed because it's so complex, so you can't really wrap your head around all the optimization rules. We need some smarter approach. So, and that was basically the original motivation for all this RPython stuff. It's basically our Python implementation of Python. That's also, of course, how the name appeared. It's Python in Python. Yeah. It's very compatible with Python 2.7. Basically, all pure Python programs that work on Python 2.7 should just work on PyPy, and hopefully they will just be much faster. It's a rather big community, so we have like 20 active developers, some more, some less. And they have, they have diverse interests. So there are people that are really into numerics, there are people that are doing web stuff, there are some people that like to write tools, and yeah, various people. It's about 60,000 lines of RPython code for the interpreter, and then another roughly 200,000 lines of code that implement various extension modules that CPython just ships with. Next slide. And so when PyPy got to the point where we managed to insert the JIT for the first time, we added the two hints that say, here's the bytecode dispatch loop, here's the jump. But then, from then on, stuff was JITted. But that still doesn't mean that every single language feature is like really optimized. So then, a continuous process was started that basically goes through all the language features from extremely common to rarer and rarer over the years, and sort of when somebody finds a program that's not very fast, we look at the trace, we say, oh, it's not fast because global lookup is slow, and then we like add some hints to the interpreter that encode the assumptions about global lookup, how global lookups are typically used in programs. And then global lookups get a little bit faster, and then we find the next feature that's not so good. And basically it's this continuous process. Very easy to add a simple JIT that doesn't help a lot, and then sort of you can improve your language in a very piecemeal fashion until you're sort of happy with the result, with the performance result. And there are basically various points on basically a gliding scale. There are various points where you can stop and say, oh, I'm happy with the 2x performance improvement that I got over a simple interpreter. That's enough for me. Or you can sort of go on and on and on and add more and more of these things and have more and more obscure features that are really faster after a while. So in PyPy, we've now, so we've been able to add a JIT since 2008 or 2009, I think. And since then, we've been in the process of sort of rewriting the interpreter a little bit, adding some hints here and there, and getting better and better. And we're concerned with relatively obscure features. So all the core language features now have sufficient hints. And here are some examples to basically give you an impression of the kind of assumptions that you can encode. And as I said, we're still discovering, new things that we can use these things for. Method calls we talked about. Global lookups are actually very similar to method calls. Basically, the assumption about global lookups are that globals are constant. They aren't, they don't have to be. We can change the global. But in practice, most globals are never new. That means we would like to add hints in such a way that the trace really just immediately uses the correct global value and has a guard that checks that global value hasn't changed. So attribute reads I will actually talk about more on the next slides. But then there's also something rather complex. That's one of the more complex optimizations we do in that way, which is that we have some very advanced, complex internal representation of lists and lists and sets that mutate on the fly at runtime, depending on the way that a specific list is used. And the observation that led to that optimization is that if you have a list that stores integers, it will typically store only integers. And once you make such a list, it's very rare that you add a non-integer later. And if you look actually at the naive way that a list of integers is represented in memory, it's really inefficient. You have an array of pointers that all point to small heap cells that are all integers, and that all store like one value in, like after a pointer dereference on some completely different way of the heap. So when you iterate over such a list and like do something with integers, you need to dereference all the pointers, you need to do type checks, and it's just not very cache friendly. And so what we did was we added a special representation for lists that recognizes the situation where all the elements of the list are integers, then switches to a more compact representation for that list that really doesn't use the boxes at all to store the list content. It really directly into the list stores the integer values, and has a special flag on the list that says, I'm a list of ints. And then when you actually trace like a loop that manipulates such a list, you get much better code. Because you get code that doesn't have to check whether the content of the element that you just read out of the list is an int. Because you already know that all elements of the list are int. So you get code that looks much closer to something that you would write in C or Java or something like that. And then, of course, if somebody adds something, a non-integer thing to that list, you have to change the internal representation of the list completely to deal with that, with the situation that you need to store a much more generic object in there. And that's very costly then, but we also figured out, we have also found out that is a very rare situation. It happens very rarely that you make a huge list of all ints and then you add a dict to it or something. That just doesn't happen. Anyway, details are not too important, but it's just sort of to give you an idea of some of the more advanced things that we do. And to scare you a little bit, let's go to the next slide. At the very first slide, I said that the approach that I'm discussing in this talk is good for complex dynamic languages. And the reason I want to show you this slide is because quite often, sort of, when one talks about dynamic language virtual machines, we talk about, say, self or Smalltalk, and those languages are really rather simple. So some of the bytecodes are not entirely trivial, but they don't do too much work. This is not true in Python. Python has bytecodes that do a lot of work, and like surprisingly much, because Python actually looks like a relatively simple language when you sort of just get to know it and write some scripts, and it looks all nice. But then when you actually start peeking below the covers, what actually happens when Python code runs is a little bit scary. And to demonstrate this principle, this slide shows sort of a slightly simplified series of steps that is done on every single attribute. So every time you call a method in Python or you read a field out of an instance, something like that happens. And so the first step is you check whether there's a special method called __getAttribute__ on that object, and if it's there, you just call it and you're done. If it's not there, which is the normal case, you look for the attribute name in the dictionary of the object, and if it's there, you can just return it. If it's not in the dictionary, then it's not an instance field. So that means it's somewhere. It has to be somewhere on the class of the object. So we walk up the method resolution order of the class of the object. Python has multiple inheritance, so there's some kind of semi-complex algorithm that puts all the transitively reachable base classes into some linear order, following the Dylan model. And basically you walk along that method resolution order and you look into every class and you see whether the method is in that dictionary. If you find an attribute, you don't just return it. Instead, you call the method on that attribute, which again will trigger parts of all that stuff again. If it's not there, you call another special method. If that special method is there, you call it. And only then you raise an error audit if all these steps don't work. So all this is one bytecode. If you write a traditional tracing did for Python, in your trace you will only see get attribute, and then it's your job to sort of produce efficient machine code from that, following all these steps that are lined out, which is obviously completely impossible. Right? So that basically, I mean, the details again are completely irrelevant, but I just want to motivate a bit why I think that, in my opinion, it's really not that tractable to sort of manually write a JIT for Python without having way too much time or way too much money or way too much pain tolerance. So because in the meta tracing approach, this mess is not a problem at all, because the meta tracer will simply, I mean, you have to implement it in an interpreter anyway, but then the meta tracer will simply follow the interpreter along through all those steps, and you can add some hints. And in the end, the code that is left after constant folding and elidable removal and stuff is usually quite simple. But you didn't have to sort of specify any complex ad hoc rules for how to generate good code for an attribute lookup anywhere. And actually, I mean, so the hints that you have to provide to make that stuff fast are again not completely non-trivial, but also not that bad, because I mean, in Python you can change the methods of the class at runtime. So it's not really, the lookup function that we saw earlier wouldn't be pure, because you can change one of the method dictionaries to get it into. So you need to be a little bit more clever. Basically what we do is we add a version number to every class. And every time you change a class, you add a method to a class, or you change a method on a class, all the version numbers of all the classes that are affected in the heap currently get their version incremented. And that means in the place where you cache a method, you can simply check, is it still the same class? Does the class still have the same version? And if not, I need to do something special. But if those two conditions are met, it's fast again. Right. Okay. Anybody wants to ask something about that?
Couldn't you just implement like an intermediate bytecode that you could actually trace that does all of this stuff? Is that just not practical for Python?
No, absolutely you could, but I mean, basically what you do then is you're shifting the complexity around, because that would mean that in the Python compiler that takes Python source code and generates bytecode, you would have to, for every method, for every attribute lookup, you would have to expand this into like 17 bytecodes, right? So that means the bytecode is a lot less compact, and instead, I mean, basically you shift the complexity out of the interpreter into the parser and bytecode compiler, and yeah, so it's possible that if you're a little bit smart about where you shift it, the end result is kind of okay, but you still need to sort of carefully think where you want to put it, right? Was there another one?
No, don't think so.
Excellent. So yeah, that is basically all I wanted to say about Python, and to actually at least make it somewhat plausible that stuff works. I have some benchmark numbers on the next slide. As you hopefully know, all benchmarks are lies. And of course, the benchmarks I have here are also lies, and they're also old lies, because the numbers are from my PhD that I handed in like 3 years ago. So by now, the numbers are probably different, but yeah, not. I mean, nothing fundamentally changed. It's probably a few percent in various directions, but sort of the general order of magnitude should still be the same. So this slide of benchmarks is a number of Python programs that we ran on various Python implementations. And the baseline that we normalized all the numbers to is CPython, which is basically the standard Python implementation that everybody uses if they say Python. And it's a very simple bytecode compiler, bytecode interpreter. It's very similar to, say, Java. It's a stack machine, nothing fancy. It's not particularly efficient. So the next implementation that we looked at was Psycho. So Psycho is actually a method-based JIT for Python that you can use, or that you could use at the time, as an extension module for CPython. It's written by one of the PyPy founders, and actually it turned out to be completely impossible to maintain, because it did all.
We were doing so well.
Is it working again?
Hopefully.
You can hear me, right?
We can hear you. Yeah.
Thanks. I was ranting about what was the last thing you heard?
You're talking about how Psycho was unattainable?
Oh. So basically, Psycho was started around Python version 2.1, I think, and then every new Python version added features, and at some point, the author of Psycho just gave up trying to add these new features to Psycho because sort of stuff was so tangled, and basically at the time there was this joke that said that Psycho consumes a brain per inch of progress. And it's kind of true. So there were like 2 other brave people that tried to get into it with sort of mixed levels of success, but nowadays it just doesn't work anymore. Right. So the next bar, which is sort of less than half the speed of CPython, is PyPy without a JIT. So it's really just taking the Python interpreter, translating it to C, adding a GC, but not adding the meta case into it at all. And okay, it's a little bit annoying that it's slower than CPython. The reason is that sort of the Python language is sort of at a somewhat higher level of abstraction than C. So a number of things are a little bit more costly. We spend a little less time to optimize the interpreter, so it's quite a bit slower. So the next step is we just add the hints that say, here is the bytecode dispatch loop. And so tracing works, but the JIT doesn't know anything anything specific about how Python is used. So, and then PyPy becomes, sort of goes back to the same level that CPython has. As fast as the bytecode interpreter, nothing fancy happens. The results aren't really that good. And then the interesting thing happens when you add all the other hints that basically say, here is how a method call is used, etc., etc. And then we get a 7.5 times speed up over CPython. Okay, so that's good. Like, just do nothing and your program gets more than 7 times faster. We like that. But then the other question that you could ask is, so we have this weird method, this weird indirect method of constructing a virtual machine. How does it stack up against like real virtual machines, whatever real is? Go to the next slide. So what I did is compare PyPy against sort of proper traditional C++-based virtual machines, V8, Lua, and Hotspot. And I used the Shula benchmark set, which is I mean, the reason to use the benchmark set is that it's basically a number of benchmarks where the same task is implemented in a wide variety of languages. So you can sort of, like, it's a fair comparison between different implementations of different languages. And here I normalized to PyPy, and we can see that V8 is about 70% faster than PyPy. I'm pretty sure that nowadays it's even much faster because Google has increased the team and added lots of, put lots of work into it. Lua did is about 2x faster, which is pretty good, given that Lua did is a one-person project, like a one genius project or something like that. And then there's Hotspot, which is like the 1,000-pound gorilla. Is it pound? Anyway, the huge hundreds and hundreds of person years virtual machine that is basically, yeah, that you need to compare yourself against, sort of. And I mean, on the one hand, you could say, okay, we're sort of twice slower, 3 times slower, but then, in a sense, I'm actually relatively happy with these results because sort of the effort that went into the JIT part, just of PyPy, is not comparable against the huge amount of effort that has gone into Hotspot. And also, now that we wrote the JIT, which, okay, was annoying, it took some years, but now that we wrote the JIT, it can be reused completely for other languages. And I'm actually going to talk about one such other language, but now I'm going to give a slightly silly demo. I mean, the problem with language demos is always that they're slightly boring, because of course when you write a new VM, you want it to behave exactly the same. So you run the same program twice, and on the one hand it takes a second, on the other hand it takes 10 seconds. Okay, but so what we started doing is we started doing sort of graphical demos to make it at least somewhat exciting. And since I'm actually using Skype on the phone, I'm going to do something even sillier, which is this. Right. The demo takes about a minute, so you don't have to stand this wobbly nonsense for long. So what this is basically a little program that opens the webcam and gets frame per frame, feeds each frame into a Python program that does a very simple Sobel edge detection, but in pure Python. So if we start that, actually I should have started that while talking. If we start that with CPython, it just takes ages. I mean, it's exactly the same program that CPython is very bad at. It's lots of arithmetic, it's 2 huge loops, it just goes over the pixels, and it just, I mean, for the first frame to appear, quite a lot of patience is needed. But actually, I mean, what I discovered is that it's worth it to wait for a little bit, because otherwise, the Python version of the demo is not actually, the PyPy version of the demo is not actually very impressive. Right, okay, so we have a frame of me, you can see some edges here, but it's not actually moving. So let's stop this again. And of course then the more fun version of the demo is with PyPy, where you can, yeah, now you see why I'm wearing this striped shirt. Right, okay, back to proper camera. Right, so just to prove that I've not been talking about a completely non-existing VM for the last 1.5 hours. Okay, very briefly, next slide, I'm going to talk about Pyrolog, just sort of to demonstrate this idea of retargetability of our JIT. So Pyrolog is one of the case studies I did to prove that the whole outpattern approach works for a very different kind of language than the typical object-oriented dynamically typed language that most VMs really care about. So who in the room actually knows some Prolog? Hey, Prolog is great. So Prolog is very, I mean, it's kind of obvious that Prolog is very different. It's a logical language. It has tail recursion, it has backtracking, it has logical variables, it doesn't have objects, it has pattern matching. So in a sense, the execution model is completely different than that of Python. So what I tried to see was, can I sort of use the same approach and still get somewhat decent performance using that JIT that we wrote for a completely different language. And it turned out that yes, in a lot of situations, Pyrolog is amazingly fast. And in some others, particularly if you write programs that are very logicy and use lots of backtracking and have completely weird non-determinism, the JIT is a little bit confused and does not produce such great code. But anyway, I mean, Pyrolog was surprisingly fun to implement. It's like 15,000 lines of R code. It supports like the core of the language, obviously, because that's tiny, but then also quite a number of built-ins. It doesn't really need that many hints. There are about 17. And the numbers are okay. Let's look at the next slide. So this is normalized to the Sixtus interpreter. So Sixtus, Prolog is one of these weird languages that still has a commercial implementation. That's very good. So that's called Sixtus. And Sixtus has two modes. One is a simple bytecode interpreter. That's what we normalize to. And then Sixtus also has the compiler. So the compiler of Sixtus is like 9 times faster than its interpreter. SWI Prolog is the biggest open source implementation. It's like 2.7 times faster than the interpreter. And then if you use just the interpreter of Pyrolog, it's at 60% of the performance of Sixtus, but the JIT sort of brings it over the open source implementation, but does not manage to beat the tuned for many years commercial Prolog implementation. Right. So any questions about Pyrolog?
How long did it take to implement that? How long was it to implement?
It's not really that easy to say because it was my bachelor's project, and I sort of kept continuously spend a couple of weeks here and there on it. I couldn't say. But the core of the language is really rather small, and it's possible and fun to sort of try small Prolog language extensions, which is really what I wanted it for originally. So in a sense, implementing just the core of it is probably not that long. I guess you can write most of it in a week or something. Yeah, is there another one? Was there a question in the back or not really?
No, I don't think so.
Okay, excellent. Okay, so now we're at the end. Next slide. So summary. Using the Python JIT, it's possible to, now that we painfully wrote it, it's possible to share the JIT, a lot of the JIT infrastructure between completely different languages, as long as you're willing to implement your language by writing an interpreter, an Python interpreter for it. And but basically, once you wrote an Python interpreter, it's enough to add a small number of hints to get a JIT, and then some more hints to sort of continuously improve performance of the JIT to a point where you're happy with it. And by now, we've really tried this approach for quite a wide variety of languages, and I'm relatively confident in saying that if your language has some kind of runtime variability and can benefit from JIT, you could probably get something out of RPython. And then sort of the motto of RPython could be that it gives you 80% of the great JIT with 20% of the effort. Then basically we can fight whether it's 80-20 or 50-50 or whatever. Yeah. Okay, that's it from my side. Thanks a lot.
More questions?
And I'm happy to take more questions.
Yep. Can you say something about the memory consumption of tracing JITs in general, or PyPy in particular?
It's actually not that obvious, because Python is a lot PyPy is a lot more memory efficient about representing all the Python objects like lists and instances and stuff like that than CPython. But then, of course, on the other hand, there is the space that you need to store the machine code that you generate. And in practice, we see both things. Sometimes we have server applications that just have huge heaps, and then are really happy with PyPy because, the huge amount of objects get smaller. But then on the other hand, we have people that say, oh, suddenly I need twice the RAM because of all the machine code that we generate. Right? I don't really know. I mean, it's not completely obvious to me that tracing JITs are generally more or less generally consume more or less memory than say method-based JITs. I mean, I don't really think that there's a general rule. I know that we had to put a lot of effort into some surprising corners in the JIT to reduce the memory consumption. For example, in the beginning, guards. I mean, there are a lot of guards, and if you implement them naively, they can. I mean, like they can use huge amounts of memory, basically. And so, I mean, at some point I said there are some annoying technical difficulties, and actually guards are one of them. It's not that, like, getting them to work is not that hard, but then making it practical that you have a lot of guards that could potentially fail, but in practice never do, took a lot of engineering effort to get the memory consumption down.
Thank you.
So I have a couple of questions.
Of course, of course.
So you've talked about generating code,
Right.
but you've never mentioned anything about invalidating or flushing code, and so I
Right.
wondered whether you had any particular framework that you used for doing that, and especially do you use speculative compilation and flushing of code to deal with assumptions which are rarely invalidated?
Right. So one refinement of the hints that I showed you today actually leads to exactly that. And that is actually, so I talked a little bit about class versions. And class version is a prime example for speculation.
Yeah,
Because basically you read the version out of the class, and usually you can expect that that never changes, right? Because in practice, it's very rare that sometimes in the middle of program execution adds new methods. So what we do is that we mark the version field of the RPython object that represents classes as a special speculating field. And that adds some machinery that if you read a field out of such a, like, if you read such a field, you don't actually produce anything in the trace. Instead, you have a special write barrier on these fields. And then you record a dependency between all the traces and all the speculatively read fields. So when you actually, the write barrier triggers and somebody changes that field, you throw away all the traces that depend on that concrete value of the field.
Okay.
Right.
Do you
So
have
yes,
to do
we-
so? Do you have, when that happens? What do you do in terms of trying to, if something is executing one of those traces, how do you get it gracefully out of the trace? The equivalent
Right,
of
so-
de-optimization in a conventional VM.
Right. So surprisingly enough, we don't really need to. When de-optimizing, we don't actually have to go and machine code to throw away the machine stack, right? What we do instead, or like fiddle around and stuff. What we do instead is, so if there's a trace on the stack and it calls something else, right? And it calls something that could potentially destroy an assumption, then that call is followed by a guard not invalidated, right?
Okay.
Which is basically a knock. But it's a knock that will be patched by a jump to some compensation code. So basically, when that call returns and the assumption was invalidated, we will immediately execute the jump and go to some incredibly annoying cleanup code that tries to figure out what went wrong and puts everything back into order. But there's no framework. We learned it all ourselves, and yes, it was annoying. I mean, I don't really see a way to get around that pain at least once, right?
Right. Okay. I was hoping you'd found a way,
No, no. I mean, I think the way we found is that you can use our method if you use our Python. But so yeah, I think that's a little bit of a philosophical point. We're fine doing hard work with doing hard work as long as it's shareable. Right? I mean, I don't think we're not trying to get rid of all the hard work. We're just trying to only have to do it once. Right.
The project, as you mentioned, has been around a long time, and early on it settled on R-Python as the language of expression and C as an intermediate language.
Right.
And in the next lecture I'm going to be talking about the choice of C and C++ as an implementation language and some VMs that have stepped away from that. I wonder, you know, is there anything you can reflect on the choices of those languages for those tasks? And you know, if you could wave a magic wand, would you still use those two languages?
So I think C as an intermediate language is a good choice. We tried to use LLVM at various points in time. Actually, the way I got into the project was to write another static backend for R-Python, for LLVM. But it turned out that actually never gave us much, right? So LLVM is not really, I mean, it's not really easier to generate than C. It doesn't have features that we need that C doesn't have. LLVM does not really produce better code than GCC. So there's not really an obvious candidate of what to use as an intermediate language. I think if we know what we know now, we might not have used R-Python. Because R-Python is, in some sense, a little bit of a weird language. I mean, it has some good properties. I mean, one of the best properties of R-Python is that it's very nicely testable, right? I mean, when we test our interpreters, we never translate. We just run the interpreter as an R-Python program and write unit tests against that. That is one of the great properties of R-Python. But then the type system can be obscure, and it wasn't really that consciously designed. It sort of grew over the years, and it has some not so nice corners, and some of the type inference errors are bad and stuff like that. So yeah, I think in a sense, some more conscious language design would have been good, but it's now. I mean, at the moment, it's not really that realistic for us to migrate somewhere else. I mean, it is, but it would be a huge amount of work, basically.
Okay.
So, just out of curiosity, which other languages will you discuss next week?
So I'm going to be talking about the implementations of things like Squeak.
Yeah.
So other implementations that go via C.
Right.
Java VMs written in Java.
Yeah.
That kind of thing.
Yeah. Actually, I think so. One very important feature and of R-Python, and I think it has that in common with the Java and Java implementation, is that R-Python is a much more analyzable language. So one problem about C is that if you look at it, it's not memory safe, and a static analysis of C cannot really give you a lot of information, right? So you, for example, using C as the language that you trace would probably be very bad, because a lot of optimizations would not be valid. In a sense, you need a kind of intermediate language that gives you a lot more guarantees in order to actually write a good optimizer. And I think that's actually the thing that I know that we absolutely need for the implementation language. It really needs to be at a certain level of abstraction to make sure that there are some guarantees that the optimizer can rely on, right?
Any more questions in the room? I have one last crazy thing which came up as you were talking earlier. The question I deferred from the middle, which is, in many user programs, there are structures that look like switches embedded in while loops, doing things like decoding images and audio and input languages. And so what about?
Or interpret.
Yeah. So meta tracing.
So I have a weird repository in a corner somewhere that tried to get that to work.
Okay.
Indeed, by trying to sort of unroll even more and try to pattern match when we were back in a similar situation.
Right.
Funnily enough, it was actually a language that's very close to, what is it called, feeling?
Feeling.
Right.
Yeah.
Basically also small and object oriented, and yeah, it's surprisingly similar. Anyway, it was very hard to get to work. I mean, it works, and the thing that kills you is warm-up time, right? I mean, because you need to double trace an interpreter.
Right.
You get huge, completely gigantic traces, and then you spend ages sort of throwing away 99% of all the observations in it to get something tiny back. But if you wait for a long time, it's not very stable, and I don't think I've found the right tool to really do that. So I think it would be very cool, but I'm not there.
Right. Okay.
You mentioned in the middle that you're implementing a racket and scheme Python implementation. Did you have to do anything special to implement continuations efficiently?
Yes, we did. So there are two approaches that the VMs typically take if you want to implement scheme. One of them is you copy stack around, right? So you write some completely scary platform-specific assembler that when you do a call to C, you really do a mem copy of exactly the right amount of C stack, copy it over to the heap, and then make sure when you copy back later, you copy back to exactly the same position, because moving it up and down is probably not going to work. That also means that call to C is not that fast. So that's one approach, and we actually considered it because we have an RPython library to do that kind of thing. But then what we actually went with, if you do that, you can write your interpreter in a naive recursive style, right? So you can map recursion at the language level to recursion at the interpreter level. But what we did instead was we completely reified all the scheme stack frames instead, right? So the interpreter is really just a loop. It never recurses. It builds heap frames, and then call to C is easy. Your frames are on the heap anyway. You just switch a pointer around and you keep running.
Right.
So that is very inefficient, usually. But then it turned out that the JIT is actually very good at just completely removing all the allocation of all those stack frames, because they're all short-lived objects. It can completely predict where they go and where they come from. So it removes their allocation, it removes all the manipulation of them, and it gives you exactly the kind of machine code that you would hope to get. Mostly.
Wow.
So this works for simple things, works amazingly well. But then sometimes you write the weird scheme things that have complex control flow and your continuation escapes or your heap frame escapes. And then you have lots of allocation and you're just very unhappy. And sort of, I'm not sure we have the perfect balance there.
Okay.
But I mean, one thing that is really satisfying to me is that if you write a really unnatural weird loop that every iteration does a call to C, the JIT will just remove all of that overhead. It runs exactly the same speed as when you just use a take call basically.
Wow. Okay.
But it's fun. I mean, basically, I went to Indiana University in Bloomington for a week, and we just wrote it. I mean, right.
Okay. If there are no more questions, I think we should thank Carl once again. Thank you.
Yep. Thanks.
We'll hang it up, and I shall send you a pointer to the video when it's
Thank you.
uploaded.
Yeah.
See ya.
Bye.